All right, so we're still going to be talking about just basic double integrals here, and let's take a look at this following integral. You got from 0 to 1, go from 0 to 3. I got x e to the xy dx dy. All right, and what happens? Well, let's try to integrate with respect to let's try to integrate with respect to x first. What happens? It's really hard. It's really freaking hard to try to integrate this guy with respect to x, because you got x e to the xy. Well, with respect to x, y is a constant, right? So it looks like we're trying to integrate something, I don't know, x e to the negative 17x, right? Like, how the hell are you supposed to integrate that, right? By parts. But we don't want to deal with parts for now. So remember, so that example was just saying I just treated y as a real constant, but really, right, y is a constant with respect to x. So, so dx dy, when you're trying to integrate this, may not be the best way to integrate it. So we want to switch the limits of integration. I want to switch the bounds. What happens if I want to say it's some double integral of something, well, of this guy, x e to xy. Well, let's say I try to do dy dx first, okay? What happens to the limits? Well, this outer bound corresponds to dy, right? And then this inner bound corresponds to dx. So it makes sense then, if I just switch dx, then my outer bound is now 0 to 3, right? Okay. Yeah, and that works. This works. This is fine. This is fine because can switch easily because the bounds are all constants. All right. We can switch these bounds easily because we're on a rectangular region where these guys are all numbers. They're all constants. So we can just switch the bounds. This becomes a huge problem later on, but let's just finish this problem now. So so we switch the bounds, 0 to 3. Now I've got to integrate it with respect to y. Well, x e to the xy, if I integrate it with respect to y first, that's actually super nice. Because what happens? Well, it becomes e to the xy, right? So it becomes e to the xy evaluated from 0 to 1. Because what's the derivative of e to the xy with respect to y? Right? What's d dy of e to the xy? Well, that's x e to the xy, right? Which is exactly what we have here. So it's actually very nice. It works out very well because now I got dx on the outside, but I'm integrating with respect to y, and this is then 0 to 3. Oh boy, what an integral sign there. E to the x minus e to the 0, right? Because e to the x times 1, and I got e to the x times 0. Okay? So that's equal to the integral from 0 to 3 of e to the x minus 1. And now I'm going to integrate this guy with respect to dx, which was the only guy remaining. I forgot it here. And what's that equal to? Well, e to the x is going to be just e to the x, and then that's minus x. And then I got to integrate it from 0 to 3. And that's equal to e to the 3 minus 3 minus e to the 0 minus 0. And so that's just e to the 3 minus 4. Okay, so you can see where switching the bounds saves the day. But I've made this huge fuss about the bounds being constant, made this an easy switch. So now let's take a look at what happens when the bounds are not constant. All right, so let's look at the following. This integral, 0 to 8, y to the 1/3, 2. Interesting. And now I got e to the x to the 4th dx dy. This is very interesting, right? Now, this guy is not a constant. It's a function, right? There's a y inside the boundary. So, again, I can just try to integrate this guy, right, with respect to dx. It's really freaking hard. You're not going to be able to integrate this guy with respect to dx. Like, how the hell do you integrate e to the x to the fourth with respect to dx. I guess you can try parts or something, but not pretty, right? So what do? I want to switch the bounds, but when you have a function like this guy in your bounds, you need to be very careful of how you switch the bounds. For example, all right, what you want to do before you switch the bounds is you want to graph this region. Right? You want to graph what that looks like. So again, y matches with the outside bounds. So you can think of this as being y is equal to 8 and this bottom bound being y is equal to 0. Right? So if we draw a picture, all right, I got y is equal to 8. Whoa. Oh, okay, we're good. Y is equal to 8, and I got y is equal to 0. Okay? And I switched up the colors. God damn it. X is equal to 8. Y is equal to 8 in red, and y is equal to 0 in red. All right, so y was red, so just forgive me. Okay? Cool. Y is equal to 8. Y is equal to 0. All right, and now x is going to be these inside bounds. So I got x is equal to 2, and I got x is equal to y to the 1/3. So I know what x is equal to 2 looks like. That looks like something like this, right? X is equal to 2. It's just vertical line at 2. But what the hell is x is equal to y to the 1/3? Well, what do you want to do? X is equal to y to the 1/3. Let's make it so I get to plot it. Let's get y is equal to something. So I cube both sides, and now I get, right, I get x cubed, or x cubed is equal to y, or you might be more familiar with y is equal to x cubed, right? So now I get this function. Woo-hoo. If I could draw and my hand doesn't tremble, yeah, that's a little bit better, right? So this is y is equal to x cubed, or as we wrote it before, x is equal to y to the 1/3. Okay, so now how do I know which region do I have? How am I sure that I don't have this region and instead of, let's say, this region right here, right? Which region do I have? Do I have the yellow region or do I have the orange region? It's not really clear. Well, the bounds tell you that too. So what you want to do then is, here's dx, right? You got dx, and what you want to do then is, when you have dx, right, the bottom variable tells you essentially, if you go from left to right, okay, if you go from left to right parallel to the x-axis, right, since this, I know this is a terrible picture, but that's the y-axis, this is the x-axis down here, right? If you go parallel to the x-axis, this tells you that you hit y is equal to 1/3 first. All right, you hit x is equal to y to 1/3 first. Essentially, you hit this first, and then you hit x is equal to 2. Right? So that means you're within this region right here. And moreover, then, you now know, since y is between 0 and 8, since you're in this region, this is going to be your shaded region. All right, so it's very, very, very important to draw pictures for these double integrals, okay? Especially when you have functions in your double integrals. So always draw pictures when you have a function in a double integral. And in fact, it's so important, I'm going to say it again, you need to draw fucking pictures when you're dealing with double integrals. In fact, sometimes it will not even give you points if you don't draw a picture. So if you have double integral, draw the picture, okay? Just listen to what I have to say. It's important. Draw the picture. All right. So that's going to be what happens when you go with dx. So now consider the following. What if I wanted to write this guy e to the x to the 4th, but now I want to do dy dx? All right. So what does that mean? So now let's pick a different color. Let's pick purple. So now here's dy, right? Wee. Okay. So the purple line is dy. And what do you notice? Well, what does y hit first, right? So on the inside, I want this inside interval, right, which is y. So that's here. This has to be y is equal to something. And this guy has also to be y is equal to something, right? And when we write the limits of the integral, we just drop the y is equal to at the end. So you'll see. So what is y equal to? What do I hit? What do I hit first with y? Well, if you look at the dy purple line, okay, I go up and I hit y is equal to 0, right? Here it is, y is equal to 0. That's what I hit first. So that means on the lower bound, I get y is equal to 0. All right? And then I keep on going up through my region, right? Through this blue region. And then I hit that boundary. But that boundary is x is equal to y to the 1/3, right? I have x is equal to y to the 1/3. I want it in a form y is equal to something. Well, we already have it up here. Right? We already have it up here. X is equal to y to the 1/3. That's the upper boundary of my purple. Right? Well, if you just cube both sides, now you got y is equal to x cubed. Okay. So this guy here is going to be y is equal to x cubed is going to be the other boundary. Okay, it's going to be the upper bound for dy. And now if we drop all this extraneous y is equal to stuff, look, those are my bounds from 0 to x cubed. And this is why I told you had to be very careful when you're changing the bounds when you had a function inside of it. Because look what happened. This guy isn't y to the, like, what the hell happened? This guy's x cubed. Where the hell do you get an x from in here, right? If you just switch both boundaries. Another very important thing to remember is that this guy on the outside, this integral on the outside, is always a constant, okay? Outside integrals are always a constant. So this integral always, God, you can't read that, can you? Let's see. Always constant bounds. Right? The outside integral always has constant bounds. So now what do I do? For dx, I still look at dx, but essentially now for dx, I just look at what's the biggest x I get and what's the smallest x I get. And we see here's the smallest x I get. It's at the origin. It's x equals 0. And the biggest x I get is right here. It's x equals 2. So here I go from 0 to 2. All right, and now I successfully switched the limits of integration. This actually becomes a lot more easier to integrate because, look, when I integrate this guy with respect to dy, it simply becomes the integral from 0 to 2 of x cubed e to the x to the 4th, all right, dx. All right, so if you integrate the y guy, the x cubed just comes down from the integrand. It's really nice. And then, now what? Now I can make a u sub. U equals x to the 4th, du equals 4x to the 3rd dx, right? So what happens? Well, here I get a 4x to the 3rd, I need to multiply 1/4 out in front. There's that dx guy. So now I get the integral of something, but I got 1/4 out in front. E to the u du, and now this is 0 to the 4th, right? Because I got to plug it in there, and this guy becomes 2 to the 4th. So it's the integral from, it's 1/4, the integral from 0 to 16 of e to the u du, and that's equal to 1/4 e to the u evaluated from 0 to 16, and e to the 16 minus 1 over 4 will be the answer to this integral. So again, this is how you switch the limits of an integral when you have a function inside. And let me be very clear, for almost any question you see on a midterm that's simply evaluate this double integral, you're going to have to switch the bounds, okay? And it's going to be like this. It's not going to be like the first case. The first case is really simple. It's going to be like this, where you have to draw the region, and then you have to figure out where the hell your bounds go and what do they change into. Like that y to the 1/3 becomes x cubed. All right. So I actually think I'm going to make another video, just more examples, I guess, of switching bounds on integrals. I think that'll be helpful, and then we will dive into 15.3. But another video on switching bounds before 15.3.